Today I want to solve the Poisson equation, and it's shown here on the screen, and you have a potential field. Here I've called it V. This is the thing you want to find, and then there's a source term, it's usually called the source term, which is kind of giving rise to the field V through this relationship. Then there is this operator in front, which is called the Laplacian. If you don't know a lot of calculus, you've probably not really encountered this before, so I'll try to explain it in kind of a qualitative way. If you're already super familiar with this equation, you can just skip ahead. So another way to write this equation is like this, where first I apply this operator. You can see it looks very similar. There's just a 2 here, and there's no 2 here. This thing is called the gradient of V, and then so you calculate the gradient of V, and then you do this operation, which is called taking the divergence. But let's try to see what that means kind of in more intuitive terms. So here is, I've attempted to draw like a contour map of the field V. And basically it's like 2 hills and then some kind of valley in between. And that is how you should imagine V. So we will only be working in 2 dimensions. So at each point in 2 dimensions, there's some kind of height associated with it. And one way you can plot this is these contour fields where the height is supposed to be constant along each line. If you think about the gradient of V, then instead of a height at each point, we have a 2-dimensional arrow. And the arrow is always pointing towards where the height is increasing. So I've drawn like a couple of examples, but you should remember that there's an arrow like at every single point. So that's what the gradient of V means. It's just an arrow pointing towards the direction in which V increases the most. Now, if we then calculate this divergence of these arrows, what does that mean? It means that now instead of arrows, we'll have single values again at each point. So here I've drawn a few examples in red. And this value will have a very large absolute value where the arrows are either coming together or going apart, like here or here. And where they are not, where there's not a convergence or a divergence of the arrows, it will be quite small, like in these points. Basically, you can think of it as a kind of counting how many arrows are going in versus how many are going out. So, back to the Poisson equation. So basically what this equation is saying, how you can read this, is that if there's a large source somewhere, a large value for the source field, it means that the potential is either at a maximum or a minimum. You can also think of it like as a 2-step process, that first we consider the force field and then the divergence of that. So then a large source term means that the force points towards or away from that point. Those two are equivalent, just different ways of thinking about it. In the end, we still want to get V. So why is the Poisson equation interesting? Well, it occurs in a lot of physical phenomena. For example, gravity, Newtonian gravity. You have Poisson equation for the gravitational potential, where the V is the gravitational energy at any point, and the source term is the mass density in space. And there's also in electrostatics, if you have electrical charges that are not moving, then this could be the electrical potential energy at any point, and this could be the distribution of charges. This equation also occurs in many other contexts, but those are just two obvious examples. So with that preamble, let's get into writing some code. I have prepared something here already, which is basic definition of some types and also some visualization using SDL2, and we're using Odin because that's what I'm using right now. So we are interested in these two-dimensional fields, so I've made a type here for that. It should have some data, which is just floating point numbers for now, and then it has a width and a height, how many grid points are there, and then it has the spacing between the grid points, which will be relevant later, most likely. Then I have a function here to make a field, which just initializes a field with some width and height and some spacing. And what I'm doing right now is I'm putting in the sine wave or a random number. Let's try with a random number and see how that looks. There's also a function to free all the allocated memory of the field. Then I define some constants for the width and height of the window. And finally there's a function to visualize the field. And we're using SDL, as I mentioned. Now, this is quite an important function, so let's spend some time going over it. I am basically drawing each pixel individually, so we perhaps don't need that square width anymore. Let's just keep it for now. So in the beginning I was drawing some squares of a certain size. I changed it so they now have size of 1 pixel. Now the data in the field can be anything, basically. So that's kind of hard to visualize. So what I'm doing is I want to rescale the data to go from 0 to 1, and that way I can more easily visualize it. So to do that, I first loop through all the values of the field, and I find the minimum value and the maximum value. Then this is not needed anymore. Then over here I loop through each pixel. I find the corresponding, so I have some I and j indices that corresponds to the row and the column, and then I find the corresponding indices in the field. And I do that by just scaling I and j by the field width over the window width and the field height over the window height. There we go, I found some bugs. Now then I want to scale it to go from 0 to 1. So what I do is, let's get the field value out actually. Like that. And then I subtract the minimum value. So now we have something that goes from 0 to maximum value minus minimum value. And then I divide that by maximum value minus minimum value. Now I have something that goes from 0 to 1. Then we have to turn that into a color somehow. Right now I just use the red and the blue channel, and depending on this value, if this is 1, I just say it's fully blue, and if it's 0, I say it's fully red, using this kind of calculation. Then I set the color to that, red, no green, blue, and 100% alpha, and then I draw a rectangle. So that's it for the visualization. Now here in main, first I make a field and then I say delete it at the end. I initialize SDL, I create a window and renderer, I have a basic event loop which is now just visualizing the field and then actually showing what's inside the renderer, and then I listen to events. So if we run this, it looks like that. Now it was just a random field, and you can see there's some bright red and bright blue, and there's some that are kind of in between. So Not sure why it's not exiting. Let's try with a sine wave. Now it looks like a sine wave going from here to here. All right. I wonder, let's try. I have both the windows open still. It's just a little bit worrying. So we should probably fix that. So here I'm looking at the event type and let's just try to print the event type. See what happens. Event type window event. There was also a mouse. Huh. That's weird. Let me go into the Odin repository and have a look. I will do that off screen. All right, I think this is the solution. We just have to get all of the events out. So we we pull all the events that were present in this frame. So now it looks like this, and it actually stops right away. Let's try to do something else, which is and also let me disable Copilot. Let's do something like this. We need some time information, so let's say time or maybe I just look in here. CPU info maybe? No. System. Okay, there's this function called getTicks, which will let us get the time, and let's just try to see how it works. So it's returning something like the number of milliseconds since we started the program. So that is good to have. Okay, so now we have a field and we can visualize it. Let's try to actually solve some Poisson equation. First, let's move this stuff to a separate file. Let's check it still works. It doesn't work because we have to import these things. Strange. Okay, there we go. So still working. And now let's keep the visualization in here. Let's make yet another file that we can call it Poisson. It's also in main. And let's just make a function called solve. So we want something that is like, let's say, output field and a source. The reason we don't return something, like we could return a pointer to a field, is because I don't want this function to do any allocations. I just, because then it's easier to control the memory use. Anyway, so how do we actually solve? Remember, it's this triangle thing, squared, output equals source, and the method we're gonna use is something called Gauss cycle, and you can look it up on Wikipedia. I'm not gonna really go through it. I'm just gonna use this equation. So there's a couple of things. This Gauss cycle works for equations like this, like AX equals B, where A is a matrix, X is a vector, B is a vector. So we have to sort of find out how to turn this equation, differential equation, into this form. So what's going to happen is that this triangle thing will be A, output will be X, and source will be B. And then we can simply use this formula and iterate a couple of times, and then we will have something that is a good solution. So, as it happens, this triangle thing is the second derivative with respect to x plus the second derivative with respect to y, and this can be turned into a matrix form since we are like working on a discretized version of space. So what I mean is that the output field is actually supposed to be like a function of x and y, but we have it just as an array. So we have something like this. And then you can approximate this thing by saying, or actually it's easier to think of it like this, by saying vxi plus 1. Let's make it a bit easier. Let's start with just this. So it's vxi plus 1 minus vxi iy. Let's make it even easier. Let's start with just the derivative with respect to x. So it would look like this. We use something called finite differences to find the derivative, to approximate the derivative with respect to x. Now there's kind of another way we could have done it, I suppose. We could have used, this is called the forward difference. We could have used the backwards difference like that. I don't think there's any real difference between those. We could also have used a central difference, which is something like this, where you have plus 1 and minus 1, but then you have to remember that the distance between them is 2 dx. But anyway, when we want to find the second derivative, what you usually do is you take this term minus this term, So let's try to do that. And this is kind of like the derivative to the right of point xi, and this derivative to the left of xi, and then the difference between those is the change in the derivative. So I can do like this, and then I have to do another dx. And now we can first of all pull this dx thing out and have dx squared, and then I can remove the parentheses here, and then have to remember to revert that one. And finally we can gather terms. And like that. So this is the final equation. And you can imagine that if we have y instead of here, then it becomes y plus 1 minus 1 and dy. So that's how that looks. Now in the Gauss-Seidel method, we only need the matrix elements. So we need the matrix elements kind of like this. And so we never need the matrix itself. So let's try to think about how those elements look. So first of all, let's try to turn this V into a vector. So we actually already know how it looks, right? Because if we go over here, it's just a flat array, which means that the data is kind of stored like this. Vx1, y1, Vx2, y1, and so on all the way to Vx with y1. And then the next one will be x1, y2, x2, y2, and so on. So if I want to do dx squared, I need to combine, let's say we're doing it for I equals 2, then I need to combine this element with that element and this element. So A is a matrix, and it will have to look something like this. Let's ignore the first row because we're interested in the derivative of the second one. Then it should have actually plus 1 of I minus 1. It should have a minus 2, that's this minus 2, and then it should have plus 1 of I plus 1. Now there's one more thing, which is that we have to remember to divide everything by dx squared, so I'll just put that out front. And then the matrix kind of looks like that. And the rest is zeros because it doesn't, the second derivative at I equals 2 doesn't know anything about any of the other points. Now what is the next one? If I equals 3, sorry, then it just looks like this. Everything is shifted over by 1. And the same thing when we go to the next one. This is something that's worth thinking about. So it's just like this tri-diagonal thing where we have -2 on the diagonal and +1 on either side. But what happens at the boundaries? Well, there's a couple of choices. You can choose to do periodic boundary conditions, or you can choose to do fixed boundary conditions. I think we're just going to do fixed for now, so we'll just pretend that nothing happens there. Do it like this. And other choices, like I said, you can do periodic boundary conditions. That's the same as putting a +1 at the very end, but we're not going to do that. So that's kind of the X part. Let's now consider how the Y part looks. It's a little bit more tricky because we have to connect things on different rows. So before we just connect the adjacent elements. Now for Y1 at X2, for example, we have to go all the way over here. So actually it will be again -2 for the same point, but we don't connect to that one, and then we don't connect to this one, but all the way over here, like with zeros later, there's a +1. Because I want to connect this guy to that guy that's all the way over here. So this is maybe not trivial, it's worth thinking about, but I won't go into too much more detail. But the basic idea is that instead of going -1 +1 column, we go plus width and minus width. So that's kind of the structure of this. So perhaps to make it easier to understand and also use, let's make a function that takes 2 indices and returns the value of the matrix element. So basically like a function that can return these things. So let's call it A, why not? And it should take an integer and an integer and return a float. And we will just ignore this prefactor and add it later. For right now it's just, should we return -2 or +1 or so on. And actually, just before we continue, we should remember that the full A matrix is the sum of these two. So if I equals j, we can return -4. If let's say I plus 1 equals j, then we should return 1. If I minus 1 equals j, then we should return 1. If I plus width, so we need a width as well, we should return 1. If I minus width equals j, we should return 1. And otherwise we should probably return 0. So let's have a width here, which is also an integer. And I think that's correct. All right. So what we need now is to try to implement this. So let's say we have a number of max iterations, could be 100, and then we will say for iteration less than max iterations plus equals 1. Then we need to do a Gauss-Seidel iteration. And the nice thing about Gauss-Seidel is you can do it in place. We also, so let's say we have an error which starts out as 0, and then I want to loop over each row. And each column. And then the index for that is column plus row times field dot width. And then the new value. So let's use this notation. So xk is equal to field at the index, and we also need b, which is now I call it, up here it was called output, but let's call it field. So it's also that guy. And then xk plus 1 is equal to this equation. So we have b minus, then we have to have something, I don't know what to call it, let's call it part 1. And we have to go from 1 to I minus 1, so that is, let's call it j. So j is less than the index. Then we have to find let's call it aij, same as here. And that is simply this function we defined up here, which is called a, index and j, and field.width. And then p1 is equal to aij times field.data at this index. Great. Then there is a second part, which goes from index plus 1 there really should be a length, but whatever. And it's the same story. So now we have performed these two summations. So now we have to say b minus part 1 minus part 2, all of that divided by a like that. And then we have to remember that these these a's don't have the dx. If you remember, there's a dx up here and a dy, but those are the same. So we have to remember to add them. Now we're also dividing here, so it doesn't really matter. Actually, the only place where it will enter is here. I've called it dg because it's equal to both dx and dy. Right, I think that's what I called it. Yes. Okay, and the final step is to assign that. Now we also want to calculate an error. So let's say that the error is xk1 minus b. And once we have looped over everything, we can ask what is the... Actually, let's do this. Let's get the average error. And if the error is less than something like that, let's just break. And that's it. Let's try to run it. There's something at 21. Okay. This is a bit annoying. How do we do that? Okay, you know what? I'm gonna change all of these ints. Okay, so now we have that running. Compiling. Now we should try to run it. So let's make a test source, which is just a procedure that returns a test field. Actually, we probably want to take the width and the height. And then we want to get a source, which is a new field. And the data is an array of floats that size. And we can also say source width, height. And we actually need this guy as well. Okay, so let's get this row column thing going again. And let's say if now they're assigned integers. It's a bit annoying. They're unsigned, I mean. Let's not make them unsigned, and let's say if we're like kind of close to the middle, then I have to cast that again. I don't know. Okay, so then that is some value. Let's make it 1. And otherwise it's just 0. Okay. So let's go to the main function now. Let's get the field first. Then let's also make a source, which is the test source with the same parameters. And then we delete it at the end. We'll visualize the field. Actually, what I should do now is to just initialize it to have value 0. It's not in this file anymore. It's in here. So I kind of assume it's already 0. So let's do that. Let's try to run this just to see. Of course, it didn't work because can I just cast this one to an int? So a lot of casting. Index 0 is out of range. So that's very interesting. Where's it even saying that? 115? It's because we never did that. And we don't need these semicolons. Let's try again. Okay, so now we have a field that's just 0. And it's black. It's quite lucky. Let us now try something. So we can try to just, so this actually solves it completely, right? But we could also abstract this and say, call it one iteration of Gauss-Seidel. Something like that. And do I... Okay. And then in here we need to do, should return an error, I guess. So we return that error, and here we'll say error is Gauss-Seidel for the field and the source, and let's try to run that. Does not compile. Line 73. Oops. Great. So that's running. So what I want to do now is visualize the field, then do one iteration of Gauss-Seidel, then actually we can do it here. That one I actually want to pull away. Then before we go much further, let's delay for like half a second. And try to run that. And for some reason I put render here, but it should be source. So that looks kind of broken. Let's just print. Let's actually see how long it takes. So T1, T2, print line. And I think that's in milliseconds. So it takes quite a long time. By the way, there's something I think I did wrong. Which is, if we go here, it shouldn't be this, it should be the absolute value. So with that, let's try to run it. And that didn't work because we have to import math. Yeah, there's still something wrong. Let's do some debug printing. Setting source to 1 at row column. We also have to import that. Okay, so it's setting it at the very end, because remember we're using a 100 by 100 grid, so that's wrong. Why is that wrong? It's because it's minus source height, and we actually have source height divided by 2. That's actually what I wanted. Great. So now it's like in the middle, and as you can see, it is kind of working. Now we have a big problem, which is that it takes a huge amount of time to actually run this function. And I wonder if there's some small optimizations we can do. Probably this inner loop should be made a bit smarter. So we know that we know that we don't care about all these values. We care about j minus 1, j plus 2, actually not j, shouldn't be called j, it should be called index. We don't care about the index itself, we should never reach that, but we do care about width and width. So because we know the structure of A, we can make this a lot simpler. So let's do that. And actually, because we're also, let's see, we have an I, so actually this side is, did it a bit wrong. It should be index, and then we can delete that. Delete that. I think that's correct, but then we can ignore actually I think we just do this. Now let's keep it as P1 and P2. So P1 is supposed to go from 1 to index minus 1. So this one should never happen. This one should never happen. Now P2 is supposed to go from index plus 1. Oops. And all the way to the end. But we can skip a lot of them, because we know they're 0. So let's see if this optimization did anything. Now Gauss-Seidel is a lot faster, but nothing seems to be happening with the solution, because we are likely missing something. Index plus 1. Let's say if P1 is greater than 0, we print it. Okay, so it does occasionally. We also have another problem. It should be multiplied by the field value. That's it. That is not it. Because it's not the field value at k, it's actually the field at right at index minus 1, and here is the field at index. So that one we should only do if index is greater than width. Otherwise we're going to end up in trouble. Actually greater than or equal to. And here I suppose we have to save index is greater than or equal to 1. And here we have to save index is less than field width, field length. Basically this. And the same here, if index plus field width is less than that. What does it say? Ah, there's no length. Why did I write length? Great. Let's try that. Okay, now something is happening, and at least it's a lot faster, which is good. But it's not quite right. Because this should not be xk, it should be the data at that index. Okay, this looks more right, it's like more circular. Let's go back here and let's remove, let's only do a 5 millisecond delay. And now we can see how quickly it's converging. Gauss-Seidel is quite fast now, which is good. And what is it? How was the color scheme again? Let's check that out. If the value is very low, then it's red. So I think that makes sense. It should be red there. We can try to play a little bit more with it. We can add another one here that says, like, how about we put one in the corner? That's weird. Maybe there's some interference here between those two. Let's put it like that. This is an else if now. I guess it's just getting relatively smaller. That's the problem. Okay, let me just fix this formatting. The one thing I don't like about Odin is that there's no formatting tool that I could find, at least. Let's remove the timing. Let's put the timing back. But let's comment it out. And this one as well. And also that thing. Now it's just running as fast as possible. So I think that is a fully fledged solver. Now we can see we have a negative area and a positive area. We could also put them, we could also do something more interesting. Let's select all of this and put it here. And we will say 10 and 10. So now there should be like a ring. Exactly. So that's kind of cool. Instead of 1, how about because the rings seem to be dominating everything. All right. So I think that's it for this video. This is just the basic solver. We can try to do some other things in another video, like adding events for clicking. So let's say if I clicked, I would add extra source terms. That could be kind of fun. Or maybe the arrow keys or something would move the source around. But yeah. Let's leave that for another video, and I'll see you in the next one. Actually, I just had one final cool idea, which is what happens if we take a random source. So now I have this function that just initializes the value of the source to a random number between -1 and 1. So if I use that instead, random source, and then we run it, you get something that looks like this once it's converged, kind of like almost like a cloud or something. So when you solve the Poisson equation, it's kind of smoothing out the noise, which I think is kind of interesting. Let's just to bring that point home, let's try to just visualize the source. It looks like this, like completely noisy, but once you solve the Poisson equation, you get something that looks a lot more pleasant. So I think that's kind of cool. And now see you in the next one.